Tonight we are going to look at something you see every single day. Something so familiar, so ordinary, so constant that you have probably never stopped to think about what it actually is. It rises in the morning, it sets in the evening. It warms your face, lights your world, grows your food, and keeps you alive. You have spent your entire life under its gaze without ever truly understanding what it is or what it is capable of. The sun, a ball of fire, 109 times wider than Earth, so massive that it contains 99.86% of all the matter in our solar system. Every planet, every moon, every asteroid, every grain of dust, all of it combined makes up less than 0.2% of the solar system's mass. The sun is not just the center of our solar system, it is the solar system. Everything else is debris. And here is what most people do not realize. The sun is not a gentle, stable, predictable star. It is a violent, chaotic, temperamental monster. A continuously detonating thermonuclear bomb, held together by its own gravity, racked by magnetic storms, so powerful they can be seen from other star systems, and prone to sudden, unpredictable outbursts that have the power to end civilization as we know it. This is not an exaggeration. This is not science fiction. This is documented scientific fact. In 1899, the sun erupted with the most powerful geomagnetic storm ever recorded. It set telegraph stations on fire. Operators were shocked by their equipment. Auroras lit up the sky over Cuba, Hawaii, and Colombia, places that had never seen northern lights before. Telegraph systems across North America and Europe failed simultaneously. And here is the part that still stuns scientists. Some telegraph operators disconnected their batteries entirely, and their machines kept working, powered by the electromagnetic current that the storm itself was inducing in the wires. That was 1859. The most advanced electrical technology on Earth was the telegraph, simple copper wires strung between wooden poles. The storm was an inconvenience, a curiosity. That was 1859, a year when the fastest form of communication was a copper wire carrying Morse code. A year when electricity was a scientific curiosity, not a civilization-sustaining infrastructure. A year when losing the telegraph meant going back to sending messages by horseback, inconvenient but survivable. The Carrington Event was named after Richard Carrington, a British astronomer who happened to be sketching sunspots on the morning of September 20, 1859, when he observed something unprecedented: two brilliant white patches of light erupting from a large sunspot group. He had witnessed a solar flare, the first ever recorded by a human observer. The flare lasted about 5 minutes. 17 hours and 40 minutes later, an extraordinarily fast transit time that tells us the resulting CME was traveling at over 2,500 kilometers per second, the geomagnetic storm struck Earth. The auroras were extraordinary. People in Colombia, near the equator, saw red and green lights in the sky. In the northeastern United States, the aurora was so bright that people woke up in the middle of the night thinking it was dawn. Newspapers reported that you could read a book by auroral light alone. Gold miners in the Rocky Mountains began preparing breakfast at 1 in the morning, convinced the sun had risen early. The effects on technology were dramatic for the era. Telegraph operators in multiple locations reported receiving electric shocks from their equipment. In some offices, the telegraph paper caught fire. And in the most remarkable detail, operators on the line between Boston and Portland, Maine, disconnected their batteries and found that the geomagnetic current alone was sufficient to power the telegraph. They sent messages back and forth for over 2 hours, using nothing but the electricity that the storm was inducing in their wires. It was the first time humans experienced a direct, tangible interaction between solar activity and terrestrial technology. Now imagine the same storm hitting today, right now, with 7 billion smartphones connected to the internet, with GPS satellites guiding every airplane, every ship, every missile, with power grids spanning entire continents, linked by thousands of kilometers of high-voltage transmission lines that would act as antennas for the geomagnetic surge, with a global financial system that processes trillions of dollars per day through electronic networks, with hospitals running on electricity, water treatment plants running on electricity, nuclear power plants running on electricity. Scientists estimate that a Carrington-class storm today would cause between $1 and $2 trillion in damage in the first year alone, and that full recovery could take 4 to 10 years. Some models suggest the death toll could reach millions, not from the storm itself, but from the cascading infrastructure failures that would follow. And in July 2012, the Sun fired a Carrington-class eruption directly through Earth's orbit. It missed us by 1 week. 1 week. If Earth had been 7 days further along in its orbit, you would know this story by heart, because you would have lived through it. Tonight, we are going to walk through 7 shocking discoveries about the star that gives us life. And that could, on any given day, take it all away. We will start at the very center, where temperatures reach 15 million degrees, and atoms are being crushed together with such force that they literally fuse into new elements, releasing the energy that powers everything on this planet. We will travel outward through layers of plasma so dense that a single photon of light takes 100,000 years to fight its way from the core to the surface. We will watch the sun's magnetic field twist and ride and snap, launching billion-ton clouds of plasma into space at millions of kilometers per hour. We will relive the night in 1989, when a solar storm plunged 6 million people into darkness in 90 seconds. We will see the photographs taken by the Parker Solar Probe, a spacecraft that has literally flown through the sun's atmosphere closer to a star than any human-made object in history. And we will look into the future 5 billion years from now, when the sun will swell into a red giant, consuming Mercury and Venus, boiling Earth's oceans, and dying in a slow, beautiful, catastrophic farewell. By the end of tonight, you are going to understand the sun in a way that changes how you look at it tomorrow morning. Not as a yellow circle in the sky, but as a living, breathing, raging nuclear engine, the most powerful and most dangerous object within 4 light years. The star that made us, and the star that will eventually unmake everything we have ever known. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let us begin. Let us start at the very beginning. Not the beginning of the sun, we will get to that, but the beginning of our understanding. Because for most of human history, we had no idea what the sun was. We knew it was bright. We knew it was warm. We knew it rose and set with a regularity that governed our entire existence. But what it actually was, that remained one of the deepest mysteries in all of science, unsolved until surprisingly recently. The ancient Greeks debated it. Anaxagoras, in the 5th century BCE, proposed that the sun was a mass of red-hot metal larger than the Peloponnese Peninsula. For this claim, which turned out to be wildly wrong in the details, but remarkably right in spirit, he was charged with impiety and exiled from Athens. The crime of trying to explain the sun scientifically rather than accepting it as a god nearly cost him his life. Other civilizations approached the sun differently. The Egyptians worshipped Ra, the sun god, who sailed across the sky each day in a boat and journeyed through the underworld each night. The Aztecs believed the sun required human blood to sustain its journey across the sky, a belief that drove some of the most elaborate sacrificial rituals in human history. In Hindu mythology, Surya rode a chariot pulled by 7 horses across the heavens. The Japanese called their nation Nihon, the origin of the sun, and their imperial family claimed descent from Amaterasu, the sun goddess. Every major civilization that has ever existed has placed the sun at the center of its cosmology, its religion, or its identity. The sun was not just observed, it was worshipped. And yet, despite this universal reverence, no one could explain what it actually was. The question of the sun's energy source remained one of the deepest mysteries in all of natural philosophy. For over 2,000 years after Anaxagoras, the question remained essentially unanswered. The sun was clearly hot. It was clearly big. But what was it made of? What powered it? In the 19th century, as the laws of thermodynamics were being formulated, the question became urgent. Lord Kelvin and Hermann von Helmholtz calculated that if the sun were powered by chemical combustion, burning in the ordinary sense, it could have lasted only a few thousand years. If it were powered by gravitational contraction, slowly shrinking and converting gravitational potential energy into heat, it could have lasted about 20 million years. But geologists and evolutionary biologists were already demonstrating that the Earth was far older than 20 million years. Darwin's theory of evolution required hundreds of millions of years at minimum. The geological record showed billions of years of history. Something was wrong. The sun was older than any known energy source could explain. The answer came in the 20th century, and it was one of the most profound revelations in the history of science. The sun is powered by nuclear fusion, the same process that powers hydrogen bombs, but on a scale so vast that it makes our most powerful weapons look like firecrackers. This is shocking discovery number 1. The engine at the heart of the sun. Deep in the solar core, where the temperature reaches 15 million degrees Celsius and the pressure is 265 billion times the pressure of Earth's atmosphere at sea level, hydrogen atoms are being crushed together so hard that they overcome their natural electromagnetic repulsion and fuse into helium. This is the proton-proton chain reaction, the process that has powered the sun for 4.5 billion years and will continue to power it for another 5 billion. Let us walk through what actually happens, because the details are astonishing. It starts with 2 protons, hydrogen nuclei, colliding with enough energy to overcome the Coulomb barrier, the electromagnetic force that makes positively charged particles repel each other. At 15 million degrees, the protons are moving so fast that they can get close enough for the strong nuclear force, which operates only at extremely short distances, to grab them and bind them together. When 2 protons fuse, one of them immediately converts into a neutron through a process called beta plus decay, releasing a positron and a neutrino. The result is deuterium, a nucleus with 1 proton and 1 neutron. This step is incredibly rare. Despite the colossal temperatures and pressures, the probability of any given pair of protons fusing is extraordinarily low. A single proton in the Sun's core will wait on average about 9 billion years before it successfully fuses with another proton. The Sun only works because it has a staggering number of protons, roughly 10 to the power of 57 of them, all trying simultaneously. It is a game of statistics played at a cosmic scale. Once deuterium is formed, it quickly fuses with another proton to create helium-3, a nucleus with 2 protons and 1 neutron. This step happens fast, typically within about a second. Then 2 helium-3 nuclei collide and fuse, producing 1 helium-4 nucleus, the common form of helium, with 2 protons and 2 neutrons, and releasing 2 excess protons back into the plasma. The net result: 4 protons have been converted into 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and energy. The energy comes from the mass difference. The helium-4 nucleus weighs slightly less than the 4 protons that created it. That missing mass has been converted into energy according to Einstein's most famous equation, E equals mc squared. How much energy? Each individual fusion reaction produces a tiny amount, about 26.7 million electron volts. But the Sun performs this reaction approximately 9.2 times 10 to the power of 37 times per second, every second. That is 92 billion fusion reactions per second. Their result is an energy output of 3.8 times 10 to the power of 26 watts. Let us try to make that number meaningful. The total energy consumption of all human civilization, every power plant, every vehicle, every factory, every light bulb on Earth is approximately 18 terawatts. The Sun produces that amount of energy in about 47 billionths of a second. In 1 second, the Sun releases more energy than humanity has consumed in all of recorded history. And here is the detail that never fails to astonish. Despite this unimaginable energy output, the Sun is remarkably inefficient. Per unit of volume, the Sun's core produces less heat than the human body. A cubic meter of the Sun's core generates about 276 watts, roughly the same as a compost heap. The Sun's power comes not from intensity, but from scale. It is not that each bit of the Sun is particularly energetic, it is that there is so unfathomably much of it. Every second, the Sun converts about 620 million metric tons of hydrogen into 616 million metric tons of helium. The missing 4 million metric tons, that is the mass that has been converted into energy. 4 million tons of matter annihilated and transformed into pure energy every single second. And the Sun has been doing this for 4.5 billion years without running out of fuel. It still has enough hydrogen in its core to continue for another 5 billion years. Now, the energy produced in the core does not immediately escape the Sun. This is where the story becomes almost surreal. The core is surrounded by a layer called the radiative zone, a region so dense that photons of light cannot travel in a straight line. Instead, each photon is absorbed by a particle, re-emitted in a random direction, absorbed again, re-emitted again, in an endless zigzag of absorption and emission. The radiative zone extends from the core to about 70% of the Sun's radius. The density of the plasma in this region is so great that a photon produced in the core takes on average approximately 170,000 years to random walk its way through the radiative zone. Think about that. The sunlight warming your face right now was generated in the Sun's core before Homo sapiens existed, before Neanderthals walked the earth. The photon that is hitting your skin tonight began its journey in an era when humanity had not yet been imagined. It spent 100,000 years bouncing from particle to particle inside the Sun before finally reaching the surface and racing to Earth in 8 minutes. Above the radiative zone lies the convective zone, and the transition between the two is one of the most important boundaries inside the Sun. It is called the tachocline, and it is the region where the Sun's magnetic field is believed to be generated. In the radiative zone below, the plasma rotates as a solid body, all parts turning at the same rate. In the convective zone above, differential rotation takes over. The equator spins faster than the poles. The tachocline is where these two rotation regimes meet, and the shearing forces at this boundary stretch and amplify the Sun's magnetic field. This is the solar dynamo, the engine that drives sunspot cycles, solar flares, and coronal mass ejections. Without the tachocline, the Sun would be magnetically quiet. No sunspots, no flares, no aurora on Earth, no threat to our power grids. The tachocline is, in a very real sense, the source of all solar weather. In the convective zone itself, energy is transported not by radiation, but by convection. Giant cells of hot plasma rising toward the surface, cooling, and sinking back down, like water boiling in a pot, but on a scale that defies comprehension. The convective zone occupies the outer 30% of the Sun's radius, and the convection patterns within it are visible on the solar surface as granulation, a pattern of bright cells separated by dark lanes that gives the photosphere a textured, almost cellular appearance when viewed at high resolution. Each granule is about 1,000 kilometers across, roughly the size of Texas, and lasts about 8 to 20 minutes before it is replaced by a new one. The bright centers are where hot plasma is rising. The dark lanes are where cool plasma is sinking back down. At larger scales, supergranulation creates cells roughly 30,000 kilometers across that persist for a day or two. These structures play an important role in organizing the Sun's magnetic field at the surface, sweeping magnetic flux toward the cell boundaries, and creating the network of magnetic concentration that eventually gives rise to sunspots and active regions. When the energy finally reaches the surface, the photosphere, it escapes into space as the light and heat we know. The photosphere is surprisingly thin, only about 500 kilometers deep, and its temperature is about 5,500 degrees Celsius. This is the visible surface of the Sun, the part you see when you look up on a clear day, though you should never look directly at it. But here is where things get strange, because above the photosphere, the temperature does something that should not happen. It goes up. This is shocking discovery number 2, the coronal heating problem, one of the greatest unsolved mysteries in physics. The Sun's atmosphere has 2 main layers above the photosphere. The chromosphere, a thin layer about 2,000 kilometers thick, where the temperature rises to about 10,000 degrees. And above that, the corona, the Sun's outer atmosphere, a vast halo of plasma that extends millions of kilometers into space. The corona's temperature is between 1 and 3 million degrees Celsius. In some regions, it exceeds 10 million degrees. Read that again. The surface of the Sun is about 5,500 degrees. The corona, which is farther from the heat source, is up to 2 million times hotter. This is like walking away from a campfire and finding that the air gets hotter the farther you go, reaching temperatures that would melt steel at a distance of 10 meters from the flames. This makes no sense. By every intuition and every basic law of thermodynamics, temperature should decrease as you move away from the heat source. The interior of the Sun is 15 million degrees. the surface is 5,500 degrees. That is a clear, steady decline. And then the corona, which is above the surface, farther from the core, is suddenly millions of degrees again. This is the coronal heating problem, and it has been one of the most stubborn mysteries in solar physics for over 80 years, since the coronal temperature was first measured in the 1940s. How does the corona get so hot? Several mechanisms have been proposed. The leading candidates are magnetic reconnection events, tiny flares called nanoflares that occur when the sun's tangled magnetic field lines snap and reconnect, releasing bursts of energy that heat the surrounding plasma. Another candidate is magnetohydrodynamic waves, specifically Alfvén waves that travel along magnetic field lines from the surface into the corona, carrying energy upward and depositing it in the outer atmosphere. The Parker Solar Probe, launched by NASA in 2018, was designed in part to solve this mystery. And in December 2024, Parker made history by flying closer to the Sun than any spacecraft before, passing within 6.1 million kilometers of the solar surface, well inside the corona itself. The spacecraft endured temperatures exceeding 1,300 degrees Celsius on its heat shield, while its instruments recorded conditions in the corona at close range for the first time. What Parker found was both illuminating and confounding. The probe detected magnetic switchbacks, sudden, sharp reversals in the direction of the sun's magnetic field, far more frequently than anyone expected. These switchbacks appear to be associated with energetic processes at or near the solar surface, and they may be related to the mechanism that heats the corona. But as of 2026, the data from Parker's closest approaches is still being analyzed, and the coronal heating problem remains officially unsolved. In July 2025, NASA released the closest ever images of the Sun's corona, captured during Parker's perihelion passage. The images show a landscape of unimaginable violence, loops and filaments of plasma arcing through magnetic fields, bright points flaring and fading in seconds, streams of charged particles racing outward at hundreds of kilometers per second. The corona is not a quiet halo, it is a war zone. There is one more feature of the Sun's atmosphere worth mentioning before we move on, because it is one of the most dramatic phenomena visible during a total solar eclipse. Solar prominences are enormous loops and sheets of relatively cool, dense plasma that hover in the corona, suspended by magnetic field lines. They can extend tens of thousands of kilometers above the solar surface, arching structures that dwarf the Earth, hanging in space like bridges made of fire. Prominences remain stable for days or even weeks, held in place by the magnetic field. But when the field destabilizes, a prominence can erupt, suddenly accelerating outward and becoming part of a coronal mass ejection. An erupting prominence is one of the most visually spectacular events in the solar system. A curtain of plasma larger than the entire planet Jupiter, tearing free from the sun's surface and hurtling into space. If you have ever seen a total solar eclipse, one of the most profound visual experiences available to a human being, you may have noticed tiny pink or red features along the edge of the darkened sun during totality. Those are prominences, visible to the naked eye only when the moon blocks the blinding photosphere and reveals the inner corona. Ancient observers described them as burning mountains or flames around the eclipsed sun, not knowing that they were seeing structures larger than worlds. Total solar eclipses, in fact, have played an outsized role in the history of science, far beyond their contribution to solar physics. For most of human history, eclipses were omens, signs from the gods, portents of disaster. The ancient Chinese believed that a dragon was devouring the sun and banged drums and shot arrows into the sky to frighten it away. The Babylonians developed sophisticated eclipse prediction cycles, the Saros cycle, a period of 18 years, 11 days, and 8 hours after which nearly identical eclipses repeat long before they understood what was causing them. For centuries, eclipses were objects of fear, wonder, and superstition. But in 1919, a total solar eclipse became the stage for one of the most important scientific experiments in history. Arthur Eddington, a British astrophysicist, organized 2 expeditions, one to the island of Príncipe off the coast of West Africa, and one to Sobral in northern Brazil to photograph stars near the sun during totality. The goal was to test Einstein's general theory of relativity, which predicted that the sun's mass would bend the path of starlight passing near it by a specific calculable amount, about 1.75 arcseconds, roughly twice the deflection predicted by Newtonian gravity. The results, announced in November 1919, confirmed Einstein's prediction. Starlight was being bent by the curvature of space-time around the sun. The headlines made Einstein a global celebrity overnight, and general relativity, one of the most revolutionary theories in the history of physics, was confirmed by observations made possible only because our moon happens to be almost exactly the right size and distance to perfectly cover the sun's disk, revealing the corona and the stars just beyond it. It is one of the most extraordinary coincidences in astronomy. The moon is about 400 times smaller than the sun, but also about 400 times closer, so the two appear almost exactly the same size in our sky. No other known planet in the solar system has a moon that produces such perfect eclipses. And from that war zone flows something that touches every planet in the solar system, something that shapes the environment of interplanetary space itself, something that, when it arrives at Earth in the right way, at the right time, has the power to bring civilization to its knees. The solar wind. This is shocking discovery number 3. The sun is not just sitting there shining. It is actively blowing itself away. Every second, the sun loses approximately 1.5 million tons of material, not as light, but as particles, a continuous stream of charged particles, mostly protons and electrons, flows outward from the corona at speeds ranging from 300 to 800 kilometers per second. At its fastest, the solar wind crosses the distance from the sun to the earth in less than 2 days. The solar wind is not uniform. It comes in 2 main varieties, the fast solar wind and the slow solar wind. The fast solar wind, traveling at speeds of 600 to 800 kilometers per second, originates from coronal holes, regions of the corona where the magnetic field lines are open, stretching outward into space rather than looping back to the surface. These open field lines act as highways, allowing plasma to escape freely. Coronal holes appear as dark patches in ultraviolet and X-ray images of the sun because they contain less hot plasma than the surrounding corona. The slow solar wind, traveling at 300 to 400 kilometers per second, originates from regions where the magnetic field is more complex and closed. The exact mechanism that produces the slow solar wind is still debated. It may escape through the edges of streamers, the helmet-shaped magnetic structures visible in the corona during solar eclipses. When fast solar wind catches up to slow solar wind ahead of it, the interaction creates a compression region called a corotating interaction region, or CIR. These compression regions can produce minor geomagnetic disturbances when they reach Earth, even in the absence of a coronal mass ejection. They are a reminder that space weather is not just about dramatic eruptions. Even the steady, everyday solar wind has structure and variability that can affect our planet. The existence of the solar wind was predicted theoretically by the physicist Eugene Parker in 1958, the same Parker for whom the Parker Solar Probe is named. At the time, most scientists believed that space between the planets was empty. Parker proposed that the corona was so hot that it could not be gravitationally contained by the sun. The outermost particles had enough thermal energy to escape, creating a continuous outflow that he called the solar wind. The idea was initially rejected. A reviewer of Parker's paper called it nonsense. But in 1962, the Mariner 2 spacecraft, on its way to Venus, directly detected the solar wind, confirming Parker's prediction. It was one of the great vindications in the history of physics. The solar wind fills the entire solar system. It creates a vast bubble called the heliosphere, a region of space dominated by the sun's outflow, extending far beyond the orbit of Pluto. The heliosphere is not a perfect sphere. It is distorted by the sun's motion through the interstellar medium, compressed on the leading edge and stretched into a long tail on the trailing side, like the wake behind the boat. The exact shape of the heliosphere is still debated. Some models suggest a comet-like tail stretching hundreds of AU behind the sun, while others propose a more spherical shape with two lobes. The boundary of the heliosphere has several distinct regions. The termination shock is where the solar wind slows from supersonic to subsonic speeds. Voyager 1 crossed this boundary in December 2004 at a distance of about 94 AU from the Sun. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind piles up and mixes with interstellar particles. And beyond that lies the heliopause, the true boundary of the Sun's domain where the solar wind pressure drops to zero and the interstellar medium takes over. Voyager 1 crossed the heliopause in August 2012 at a distance of 121 AU, becoming the first human-made object to enter interstellar space. Voyager 2 followed in November 2018, crossing at 119 AU, and its working plasma instruments revealed that the transition was sharper and more abrupt than anyone expected, with the solar wind dropping to zero over a distance of less than a single AU. When the solar wind encounters Earth, it interacts with our planet's magnetic field, the magnetosphere. Earth's magnetic field deflects most of the solar wind around us like a rock in a stream. The solar wind compresses the magnetosphere on the sunward side and stretches it out into a long tail on the night side. The boundary where the solar wind meets the magnetosphere is called the bow shock, a standing shock wave in space similar to the shock wave in front of a supersonic jet. Some solar wind particles do get through. They enter the magnetosphere at the polar cusps, openings near the magnetic poles where the field lines dip down toward the surface. These particles follow the magnetic field lines downward, collide with atoms and molecules in the upper atmosphere, and cause them to glow. This is what creates the aurora, the northern and southern lights. The colors of the aurora tell you which atmospheric gases are being excited. Green and red come from oxygen atoms. Blue and purple come from nitrogen molecules. The altitude determines the color too. Green auroras occur at lower altitudes, around 100 to 300 kilometers up, while red auroras occur higher, at 300 to 400 kilometers. The result is a curtain of light rippling and shimmering across the polar sky, one of the most beautiful natural phenomena on Earth, and a visible reminder that we live inside the extended atmosphere of a star. Under normal conditions, The solar wind is manageable. Earth's magnetic field and atmosphere protect us admirably. We see pretty auroras near the poles and go about our lives. But the auroras deserve a moment of our attention because they are one of the most remarkable visual phenomena in the natural world, and their beauty masks their violence. When charged particles from the solar wind funnel down along Earth's magnetic field lines and enter the upper atmosphere, they collide with atmospheric molecules at speeds of hundreds of kilometers per second. Each collision transfers energy to the atmospheric molecule, exciting its electrons to higher energy states. When those electrons fall back to their ground state, they release the excess energy as photons of visible light. Billions upon billions of these individual atomic transitions happening simultaneously across hundreds of kilometers of atmosphere create the luminous curtains and arcs that we call the aurora. The patterns of the aurora are shaped by the magnetic field. The electrons follow the field lines downward in sheets and spirals, creating the characteristic curtain-like shapes that ripple and fold as the field fluctuates. When the solar wind intensifies, during a geomagnetic storm for instance, the auroral oval expands toward the equator, and the aurora becomes visible at lower latitudes. During the May 2024 storm, people in Mexico City, northern India, and southern Japan saw auroras, many for the first time in their lives. If you have ever stood beneath a full auroral display, you know that photographs do not do it justice. The aurora moves, it breathes. Curtains of green light roll across the sky like waves breaking on a cosmic shore. Shafts of red and purple fire shoot straight up toward the zenith, then fade, then reappear somewhere else. The entire sky becomes a canvas, painted in real time by the brush of the solar wind against the shield of Earth's magnetic field. It is, without exaggeration, one of the most beautiful things a human being can witness. And every photon of that beauty was born in violence, in the thermonuclear furnace of the sun, launched outward as a particle of solar wind, deflected by Earth's magnetic shield, and finally spent in a single flash of light in the upper atmosphere. The aurora is a reminder that we live inside the ecosystem of a star, that the sun's influence does not end at the edge of its visible disk, that we are every moment bathed in the sun's breath. But the solar wind is not always normal. Sometimes the sun does something far more violent. This is shocking discovery number 4. The sun can kill us. And it has tried. The surface of the sun is laced with magnetic fields. The sun is not a solid body. It is a rotating ball of plasma, and different latitudes rotate at different speeds. The equator completes a rotation in about 25 days, while the poles take about 35 days. This differential rotation stretches and twists the magnetic field lines that are embedded in the plasma, winding them tighter and tighter over time. When magnetic field lines become too twisted, too tangled, too stressed, they can snap. And when they snap, they release their stored energy in a sudden, violent burst. This is a solar flare, a flash of electromagnetic radiation that can span the entire electromagnetic spectrum, from radio waves to gamma rays, released in minutes or even seconds. Solar flares are classified by their X-ray intensity on a logarithmic scale. Each class is 10 times more powerful than the one below it. The weakest are A-class and B-class, barely detectable. C-class flares are minor. M-class flares are moderate and can cause brief radio blackouts on the sunlit side of Earth. And X-class flares are the most powerful, each one releasing the equivalent of billions of nuclear bombs. The X-class scale is itself open-ended. An X1 flare is 10 times more intense than an M1 flare. An X10 is 10 times an X1. The most powerful flare ever recorded by modern instruments occurred on November 4, 2003, during the so-called Halloween storms. It was so intense that it saturated the detectors, but subsequent analysis estimated it at approximately X45. For context, the May 2024 storm included an X8.7 flare, the strongest of solar cycle 25 at the time. And in October 2024, the Sun produced an X9.0 flare, one of the most powerful in decades. The energy released by a major X-class flare is difficult to comprehend. An X-ton flare releases approximately 10 to the power of 25 joules, equivalent to about 2.5 billion megatons of TNT. The largest nuclear weapon ever detonated, the Tsar bomba, yielded about 50 megatons. A single major solar flare releases more energy than 50 million Tsar bombas. The flare itself, the burst of electromagnetic radiation, reaches Earth at the speed of light, arriving in about 8 minutes. Radio blackouts occur almost immediately on the sunlit side of the planet, as the intense X-ray and ultraviolet radiation ionizes the upper atmosphere and disrupts radio wave propagation. High-frequency radio communications used by airlines for transoceanic flights and by military organizations worldwide can be blacked out for hours. But flares are not the most dangerous thing the Sun can do. That distinction belongs to coronal mass ejections, CMEs. A CME is not a flash of light, it is a physical eruption. 1 billion tons of magnetized plasma hurled into space at speeds that can exceed 3,000 kilometers per second. If a solar flare is a camera flash, a CME is a cannonball. When a CME is aimed at Earth and conditions are right, or more accurately wrong, the results can be catastrophic. The magnetized plasma of the CME interacts with Earth's magnetic field, compressing and distorting it. If the CME's magnetic field is oriented opposite to Earth's, a condition called a southward interplanetary magnetic field, the two fields can reconnect, opening the magnetosphere and allowing a torrent of energetic particles to pour into Earth's inner magnetic environment. The result is a geomagnetic storm. Geomagnetic storms induce electric currents in any long conductor on Earth's surface: power lines, pipelines, railway tracks, undersea cables. These are called geomagnetically induced currents, or GICs. In a moderate storm, GICs cause minor fluctuations. In a severe storm, they can overload transformers, the massive and expensive devices that step voltage up and down in the power grid. The danger of GIC is not that they are large in absolute terms, they are typically tens to hundreds of amperes, but that they are quasi-DC, meaning they flow in one direction for extended periods. Power transformers are designed for alternating current, which reverses direction 60 times per second in the US and 50 times per second in most of the rest of the world. When a quasi-DC current flows through a transformer, it biases the magnetic core, causing it to saturate on each half cycle of the AC waveform. This saturation draws enormous reactive currents, generates extreme heat in the transformer windings and core, and can cause the transformer to overheat and fail in minutes. The problem with transformers is that they are difficult to replace. Large high-voltage transformers are custom-built, weigh hundreds of tons, take months or years to manufacture, and there are very few spare ones available anywhere in the world. If a severe geomagnetic storm destroys dozens or hundreds of transformers simultaneously across a continent, the power grid does not just go down for a few hours or days, it goes down for months, possibly years. And that is not a theoretical scenario. It has already happened on a smaller scale. On March 14, 1989, a coronal mass ejection struck Earth's magnetosphere. The resulting geomagnetic storm was intense but not exceptional. It was rated G5, the highest level on the geomagnetic storm scale, but nowhere near the magnitude of the Carrington Event. It was a strong storm, not a record-breaking one. In 90 seconds, the entire power grid of Quebec, Canada, collapsed. 6 million people lost electricity. It was the middle of March, winter in Quebec, temperatures were well below freezing. Heating systems stopped, traffic lights went dark, water treatment plants shut down. The Montreal metro stopped running. Hospitals switched to emergency generators, which have limited fuel and are not designed for prolonged operation. The cause: geomagnetically induced currents tripped the protection circuits on 7 static VAR compensators on the Hydro-Quebec grid simultaneously. Without those compensators, voltage collapsed, cascaded through the network, and the entire grid went down in less than 2 minutes. The blackout lasted 9 hours in most areas, longer in others. Schools were closed, businesses shut down. People were trapped in elevators and on subway trains. In a province where winter temperatures regularly dropped to -20 or -30 degrees, the loss of electric heating was not merely an inconvenience, it was a threat to life. Elderly and vulnerable residents were at particular risk. Emergency services were stretched thin, operating on generator power that was designed for minutes or hours, not for the better part of a day. What made the Quebec blackout particularly alarming was how quickly the cascade occurred. The protective systems on the grid, the devices specifically designed to prevent cascading failures, were themselves triggered by the geomagnetically induced currents. The protection system did not fail. It worked exactly as designed. It detected abnormal conditions and disconnected equipment to prevent damage. But the abnormal conditions were so widespread, affecting so many components simultaneously, that the protective disconnections themselves caused a cascade. The grid was brought down by its own safety systems, overwhelmed by a threat they were never designed to handle. The Quebec blackout was, in retrospect, a dress rehearsal. A small-scale preview of what a Carrington-class event would do to a modern, interconnected, electricity-dependent civilization. The lessons should have been obvious. Some were learned, many were not. Hydro-Quebec estimated the damage at over 13 million Canadian dollars in direct costs, with total economic impact many times higher. And this was a moderate storm affecting a single province. Now imagine a Carrington-class event, a storm estimated to be roughly 10 times more powerful than the 1989 Quebec storm, not hitting one province, but the entire northern hemisphere simultaneously. Power grids across North America, Europe, and Asia overloaded at once. Hundreds of high-voltage transformers destroyed. Satellite electronics fried. GPS systems degraded or offline. Radio communications blacked out. The internet, which relies on satellites, undersea cables, and powered data centers, severely disrupted or down entirely. A study by the National Academy of Sciences estimated the economic impact of a Carrington-class event at between $1 and $2 trillion in the first year alone. The recovery time for the power grid, 4 to 10 years in the worst-case scenario. During those years, regions without power would face cascading failures in water supply, food distribution, medical care, financial systems, and social order. This is not speculative doomsaying. This is the consensus estimate of mainstream scientists and engineers who study space weather professionally. And the May 2024 solar storm gave us a taste of what is possible. Between May 10 and 12, 2024, the Sun unleashed a barrage of coronal mass ejections that triggered the strongest geomagnetic storm in over 20 years. Auroras were visible as far south as Mexico, northern India, and the Canary Islands. GPS accuracy was degraded worldwide. High-frequency radio communications were disrupted. Precision agriculture systems failed during planting season, causing an estimated $500 million in damage to American farmers alone because GPS-guided tractors could not maintain their precise planting lines. The May 2024 storm was rated G5, the same level as the 1989 Quebec event. It was strong, but it was not a Carrington-class event, not even close. It was a warning shot, a reminder. And in January 2026, the Sun released the largest solar radiation storm in over 20 years. An S4-rated event that forced astronauts on the International Space Station to take shelter and disrupted satellite communications worldwide. The Sun is currently near or at its solar maximum, the peak of its approximately 11-year cycle of activity, and it is more active than many scientists expected. The question is not whether a Carrington-class event will happen again. It is when, and whether we will be ready. Let us dwell on the 2012 near miss for a moment, because its details are chilling. On July 23, 2012, a massive coronal mass ejection erupted from the Sun. It was a Carrington-class event, comparable in speed and intensity to the 1859 storm. The CME crossed the Sun-Earth distance in just 17.6 hours, meaning it was traveling at over 2,400 kilometers per second. Had it hit Earth's magnetosphere, the resulting geomagnetic storm would have been extraordinary. But it missed. Earth was not in the path of the CME. The eruption passed through a point in Earth's orbit that our planet had occupied just 1 week earlier, 7 days. That was the margin. A study published in the journal Space Weather estimated the probability of a Carrington-class event hitting Earth in any given decade at about 12%. Over a period of 50 years, the probability rises to about 50%. These are not comfortable odds, and we have done remarkably little to prepare. Some progress has been made. NOAA's Space Weather Prediction Center monitors solar activity and issues warnings when significant CMEs are detected. Power grid operators in some countries have developed protocols for managing geomagnetically induced currents. The European Space Agency's Vigil mission, planned for the late 2020s, will orbit at the Sun-Earth L5 Lagrange point, providing a side-on view of CMEs heading toward Earth that could give us up to 5 days of advance warning compared to the current 15 to 60 minutes we get from spacecraft at the L1 point directly between Earth and the Sun. But the fundamental vulnerability remains. Our power grids, our satellite constellations, our communication networks, the critical infrastructure of modern civilizations, were built without serious consideration of space weather. And the cost of hardening that infrastructure against a Carrington-class event, while significant, would be a fraction of the cost of recovering from one. A 20-something study estimated that protecting the US power grid from extreme geomagnetic storms would cost between $10 and $30 billion, expensive but less than 2% of the estimated recovery cost of a $1 trillion event. We are, in essence, gambling, betting that the next Carrington-class event will miss us, as the 2012 event did, rather than investing in protection now. It is a bet we will eventually lose. The only question is when. Now, let us talk about something beautiful that emerges from all this violence. Because the sun's magnetic activity does not just produce storms and destruction, it also produces patterns, rhythmic, predictable patterns that have fascinated scientists for centuries. This is shocking discovery number 5. The sun has a heartbeat. In 1843, a German astronomer named Samuel Heinrich Schwabe noticed something remarkable after 17 years of careful daily observations of the sun. The number of sunspots, dark patches on the solar surface caused by intense magnetic field concentrations, was not random. It rose and fell in a regular cycle of approximately 10 years. Later refinements extended this to about 11 years. Sunspots themselves had been observed through telescopes since the early 1600s. Galileo was among the first to study them systematically. They appear dark because they are cooler than the surrounding photosphere, about 3800 degrees Celsius compared to 5500. The strong magnetic fields within a sunspot inhibit convection, preventing hot plasma from rising to the surface and creating a relatively cool, dark patch. But the sunspot cycle is more than just a variation in the number of dark spots. It is a complete magnetic cycle that reverses the sun's magnetic polarity every 11 years, meaning the full magnetic cycle is actually 22 years. At the beginning of each cycle, sunspots tend to appear at higher latitudes, around 30 to 40 degrees north and south. As the cycle progresses, they migrate toward the equator. By the end of the cycle, new sunspots from the next cycle begin appearing at high latitudes again, overlapping briefly with the last spots of the old cycle. This pattern, when plotted on a diagram with latitude on the vertical axis and time on the horizontal axis, produces a distinctive shape that astronomers call the butterfly diagram, because the clusters of sunspot activity at each latitude look like the wings of a butterfly, converging toward the equator over the 11-year cycle. The sunspot cycle drives the frequency and intensity of solar flares and CMEs. During solar maximum, the peak of the cycle, when sunspot numbers are highest, the sun is at its most active and most dangerous. During solar minimum, it is relatively quiet. We are currently in solar cycle 25, which began in December 2019 and has been more active than many forecasts predicted. The initial forecast from NOAA and NASA suggested that cycle 25 would be relatively weak, similar to the modest cycle 24 before it. Instead, cycle 25 has consistently exceeded predictions. The sunspot numbers in 2024 and early 2025 surpassed the forecast by a wide margin, and the cycle appears to be producing one of the stronger solar maxima in recent decades. This is a reminder of how poorly we understand the solar cycle's variability. Our predictive models are good enough to identify the approximate timing of maxima and minima, but they often fail to predict the amplitude, the strength of the upcoming cycle. The sun regularly surprises us, and each surprise carries real-world consequences for satellite operations, astronaut safety, power grid management, and communication systems. The sunspot cycle also influences the amount of ultraviolet radiation the sun emits. During solar maximum, the sun produces significantly more UV light than during solar minimum. This UV variation is too small to directly affect surface temperatures on Earth, but it has a measurable effect on the chemistry of the upper atmosphere, particularly on ozone concentrations. Some researchers have explored connections between the solar cycle and patterns of weather and climate variability on Earth, though these connections remain subtle and controversial. But the sunspot cycle is not perfectly regular. Its length varies from about 9 to 14 years. Its intensity varies from cycle to cycle. Some maxima are fierce, with hundreds of sunspots visible at once, while others are mild, with far fewer. And sometimes the cycle seems to stop altogether. The most famous example is the Maunder minimum, a period from roughly 1645 to 1715, during which sunspots nearly vanished. For 70 years, astronomers observed almost no sunspots. During one 30-year stretch, fewer than 50 sunspots were recorded, compared to the typical 40 to 50,000 during a normal 30-year period. The Maunder minimum coincided with the coldest part of the Little Ice Age, a period of unusually cold temperatures across Europe and North America. The Thames froze regularly. Baltic Sea ice was extensive. Crop failures were widespread. The connection between the absence of sunspots and the cold temperatures is still debated. The Little Ice Age had multiple causes, including volcanic eruptions and changes in ocean circulations, but most scientists agree that the sun's reduced output during the Maunder minimum contributed to the cooling, if only modestly. The Maunder minimum raises a disturbing question. Could it happen again? Could the sun's magnetic cycle shut down for decades, altering Earth's climate? Or conversely, could the sun enter a period of unusually high activity, increasing the frequency of dangerous space weather events? We do not know. Despite decades of study, we still do not fully understand what drives the solar cycle. The dynamo theory, which explains the cycle as a consequence of the interaction between the sun's differential rotation and its magnetic field, captures the broad outlines but fails to predict the details. We cannot reliably forecast whether the next solar cycle will be strong or weak, or whether the sun might enter another Maunder minimum. Our ability to predict solar behavior is, in some ways, no better than our ability to predict earthquakes. And that uncertainty is itself a kind of discovery, a reminder that the star we depend on for everything is, in many fundamental ways, still a mystery to us. There is something else about the Maunder minimum that deserves attention, something that connects the sun's behavior to broader questions about climate and civilization. During the coldest years of the Little Ice Age, the social consequences were severe. In Europe, crop failures led to famine. The Baltic Sea froze so thoroughly that armies marched across it. The Thames froze regularly in London, leading to the famous frost fairs where Londoners set up markets and entertainment on the ice. Vineyards in England and northern France failed. Migration patterns shifted. Political instability increased. We do not know for certain how much of this was caused by reduced solar output versus volcanic eruptions, ocean circulation changes, and other factors. The climate system is complex, and isolating the sun's contribution is difficult. But the Maunder minimum is a powerful reminder that even small changes in the sun's behavior can have outsized effects on human civilization. We have built our entire agricultural system, our cities, our economies, around the assumption that the sun's output is stable, and for the most part it is. But for the most part leaves room for exceptions, and exceptions, in the case of the sun, can reshape history. There is also the opposite concern. Some studies have investigated whether the sun could enter a period of abnormally high activity, a grand maximum, producing more frequent and intense storms. The medieval period, roughly 1100 to 1250 CE, appears to have been such a time, with higher than average solar activity coinciding with the medieval warm period. Whether the sun's current behavior is within normal bounds or trending toward something unusual is a question that keeps solar physicists busy and occasionally worried. Let us now travel to the sun, literally, because in 2018, humanity did something that would have seemed like fantasy just a generation ago. We launched a spacecraft to fly through the atmosphere of a star. This is shocking discovery number 6. We have touched the sun. The Parker Solar Probe was launched on August 12, 2018, on a mission that many engineers initially thought was impossible. The plan: use a series of gravitational slingshots around Venus to gradually shrink the spacecraft's orbit, bringing it closer and closer to the sun with each pass until it was flying through the corona itself, the outermost layer of the sun's atmosphere, where temperatures exceed 1,000,000 degrees. The challenges of building Parker were immense. How do you build a spacecraft that can survive inside the atmosphere of a star? The answer required decades of advances in material science, thermal engineering, and orbital mechanics. The mission uses Venus gravity assists, 7 of them over the course of the mission, to gradually reduce the spacecraft's orbital distance from the sun. Each Venus flyby redirects Parker's trajectory, bending its orbit and shrinking its closest approach to the sun. Without these gravity assists, the amount of rocket fuel required to reach the sun's corona directly would be prohibitive. Counterintuitively, it takes more energy to fly into the sun than to fly out of the solar system, because you have to cancel out Earth's orbital velocity of 30 kilometers per second. The key to Parker's survival is its heat shield, the Thermal Protection System, or TPS. It is a sandwich of carbon composite materials, just 11.4 centimeters thick, that faces the sun during each close approach. The front of the shield reaches temperatures of approximately 1370 degrees Celsius, hot enough to melt most metals. But behind the shield, the spacecraft and its instruments are maintained at roughly room temperature, around 30 degrees Celsius. The temperature difference across those 11 centimeters is over 1300 degrees, one of the steepest thermal gradients ever engineered. On December 1st, Itianidis 1st, Christmas Eve, Parker made its closest approach yet, passing within 6.1 million kilometers of the sun's surface. At that distance, the spacecraft was traveling at approximately 692,000 kilometers per hour, fast enough to fly from New York to Tokyo in less than a minute. Parker's solar probe became the fastest human-made object in history. Let us put that distance in perspective. The sun's radius is about 696,000 kilometers. Parker flew to within 6.1 million kilometers of the surface, meaning it was at a distance of about 8.8 solar radii from the center. It was well inside the corona, immersed in the sun's extended atmosphere, flying through plasma heated to millions of degrees. And in July 2025, NASA released images captured during that flyby, the closest photographs of the sun ever taken. They show coronal streamers, vast filaments of plasma extending outward from the sun's surface, shaped by magnetic field lines. Bright points flare and fade, tiny explosions of magnetic energy, each one releasing more energy than millions of nuclear weapons. The images are hauntingly beautiful, like watching a living thing breathe. The corona is not static, it is dynamic, turbulent, alive with energy. Parker's instruments have also revealed surprises about the solar wind. Close to the sun, the solar wind is not the smooth, steady flow that scientists expected. It is bursty, gusty, full of sudden accelerations and decelerations. The magnetic switchbacks, those sharp reversals in the magnetic field directions, are far more common near the sun than farther out. They appear to originate near the solar surface, possibly from small-scale magnetic reconnection events in the photosphere. One of the most significant findings from Parker is what it did not find. The probe was expected to detect clear evidence of the mechanism that heats the corona, the long-sought solution to the coronal heating problem. But so far, the data has not pointed clearly to any single mechanism. Instead, it suggests that multiple processes may be at work simultaneously. Nanoflares, wave heating, magnetic reconnection, all contributing to the coronal temperature in ways that are difficult to disentangle. Parker Solar Probe will continue to make close approaches through 2025 and into 2026, gathering more data with each pass. Scientists hope that the accumulated observations will eventually crack the coronal heating mystery. But even if they do not, Parker has already accomplished something remarkable. It has shown us the sun as we have never seen it before, up close, in detail, in all its terrifying beauty. The Parker Solar Probe is named after Eugene Parker, the same physicist who predicted the solar wind in 1958 and was initially ridiculed for it. Parker lived to see the launch of the spacecraft bearing his name. He passed away in March 2022 at the age of 94, knowing that the probe he inspired was on its way to confirm and extend his life's work. It is one of the finest tributes in the history of science, a spacecraft touching the sun, carrying the name of the man who first understood that the sun reaches out to touch us. Now, let us look at the sun's past and its future. Because the sun has not always been as it is now, and it will not remain this way forever. But before we talk about the sun's death, let us talk about its birth, because the story of how the sun formed is itself a tale of violence and transformation that echoes across the galaxy. The sun was born in a molecular cloud, a vast, cold region of interstellar space filled with hydrogen and helium gas laced with tiny grains of dust. These clouds can be enormous, spanning hundreds of light years and containing enough material to form thousands of stars. They are among the coldest places in the universe, temperatures as low as 10 to 20 Kelvin, just 10 to 20 degrees above absolute zero. In their frigid interiors, atoms move sluggishly, gravity dominates, and the conditions are ripe for collapse. Something triggered the collapse of the particular region that would become our solar system. The leading candidates are a shock wave from a nearby supernova, the explosive death of a massive star, or the compression wave from a spiral density wave in the Milky Way's disk. We have indirect evidence for the supernova trigger. Certain isotopic ratios in primitive meteorites suggest that radioactive elements produced in a supernova were present in the solar nebula, meaning a massive star must have exploded nearby within a few million years of the sun's birth. If this is true, it means the sun's existence, and by extension our existence, was made possible by the death of another star. A star that lived fast, burned through its fuel in a few million years, and exploded, seeding the surrounding gas cloud with heavy elements and sending a shock wave through it that triggered the gravitational collapse that formed our sun. We owe our existence not just to the sun, but to the anonymous star that died so the sun could be born. The collapse proceeded quickly by astronomical standards. Within about 100,000 years, the central region had contracted enough to form a protostar, a hot, dense ball of gas radiating energy from gravitational compression. The protostar was surrounded by a disk of leftover material, the protoplanetary disk, from which the planets would eventually form. For roughly 50 million years, the protostar continued to contract, growing hotter and denser until the temperature at its core reached about 10 million degrees Celsius, the threshold for hydrogen fusion. The proton-proton chain ignited. The Sun was born. The outward pressure from nuclear fusion balanced the inward pull of gravity, and the Sun settled into the stable configuration it has maintained for the last 4.5 billion years. The young Sun was different from the Sun we know today. It was slightly smaller, about 30% dimmer, and far more magnetically active. Its rotation period was only a few days compared to the current 25 days at the equator. This rapid rotation generated a powerful magnetic field that drove intense solar wind and frequent, violent flares, far more powerful than anything the modern Sun produces. The young Sun was, in astronomical terms, a temperamental teenager. This intense early activity has implications for the early history of Earth and Mars. The powerful solar wind of the young Sun would have battered any planets in the inner solar system, stripping away atmospheres and bombarding surfaces with energetic particles. Earth survived because it had a strong magnetic field powered by its large convecting iron core. Mars, as we discussed in a previous journey, was not so fortunate. Over hundreds of millions of years, the Sun's rotation slowed, braked by the interaction between its magnetic field and the solar wind, and it settled into the calmer, more predictable star we know today. But even in its maturity, as we have seen tonight, the Sun is far from gentle. This is shocking discovery number 7. The Sun is dying. Slowly, majestically, inevitably, but dying. The Sun formed approximately 4.6 billion years ago from the gravitational collapse of a molecular cloud, the same cloud that formed the rest of the solar system. In its earliest stage, before nuclear fusion ignited, it was a protostar, a hot, dense ball of gas still contracting under gravity, radiating energy from gravitational compression alone. When the temperature and pressure at the center reached the threshold for hydrogen fusion, the Sun entered the main sequence, the stable phase of stellar life where it has spent the last 4.5 billion years. On the main sequence, the Sun is in a state of equilibrium. The outward pressure from fusion energy exactly balances the inward pull of gravity. It is a battle that has been perfectly balanced for longer than life has existed on Earth. But the balance is not static. It is slowly, inexorably shifting. As the Sun fuses hydrogen into helium in its core, the core composition changes, helium ash accumulates, increasing the core's density and temperature. The higher temperature increases the fusion rate, which increases the Sun's luminosity. The Sun today is about 30% brighter than it was when it was born. This fact creates one of the most puzzling problems in planetary science, the faint young Sun paradox. If the Sun was 30% dimmer 4 billion years ago, Earth should have been frozen solid. The reduced solar luminosity would have put Earth's surface temperature well below the freezing point of water. And yet, geological evidence clearly shows that liquid water existed on Earth's surface at least 3.8 billion years ago, possibly earlier. The oldest sedimentary rocks, the oldest chemical signatures of water-rock interactions, the oldest microfossils, all point to a warm, wet early Earth. How did a planet orbiting a dim young Sun manage to stay warm enough for liquid water? The leading explanation is that the early atmosphere was rich in greenhouse gases, carbon dioxide, methane, and possibly water vapor, in concentrations far higher than today. These gases trapped enough heat to compensate for the weaker sunlight. Some models suggest early CO2 levels were hundreds or even thousands of times higher than pre-industrial levels. Others invoke methane produced by early microbial life as a key warming agent. The faint young sun paradox remains an active area of research, and its resolution has implications not just for understanding Earth's history, but for assessing the habitability of planets around other stars, particularly young stars that, like our young sun, may be significantly dimmer than their mature counterparts. In 1 billion years, the sun will be about 10% brighter than it is now, enough to dramatically increase Earth's surface temperature, potentially making our planet uninhabitable for complex life. In about 5 billion years, the hydrogen fuel in the core will be exhausted. The core, now composed almost entirely of helium, will begin to contract under its own gravity, because there is no longer any fusion energy to support it. As the core contracts, it heats up, and the temperature in the shell of hydrogen surrounding the core rises to the point where hydrogen fusion ignites in a shell around the inert helium core. This shell burning produces more energy than the core fusion ever did. The outer layers of the sun, pushed outward by the increased radiation pressure, will begin to expand. The sun will swell enormously, its radius growing by a factor of more than 200. Its surface temperature will drop, giving it a reddish color. The sun will become a red giant. The expansion will not be sudden. It will unfold over hundreds of millions of years. The sun will not explode outward like a balloon being inflated. It will swell gradually, like bread rising in an oven. Over the course of several 100 million years, the sun's radius will increase from its current 700,000 kilometers to over 150 million kilometers, roughly the current distance from the sun to Earth. Its surface will cool from 5,500 degrees to about 3,000 degrees, giving it a deep red color. But despite the lower surface temperature, its total luminosity will be enormous. The sheer surface area of the bloated red giant will radiate thousands of times more energy than the current sun. During this expansion, the sun will lose mass at a prodigious rate. The intense radiation pressure and the vigorous stellar wind of a red giant will strip away the outer layers of the sun, sending them billowing outward into interplanetary space. The sun may lose as much as 30 to 40% of its current mass before the red giant phase is over. This mass loss has a crucial consequence. As the sun gets lighter, its gravitational hold on the planets weakens, and the planet's orbits expand outward. At its maximum extent, the red giant sun will be so large that its outer layers will extend beyond the current orbit of Venus. Whether it will actually engulf Earth is a question that is still debated. As the sun expands, it also loses mass through an intense stellar wind, which weakens its gravitational pull and allows the planets to drift outward. Earth may migrate to a wider orbit, escaping engulfment, but it will not escape the heat. The sheer luminosity of the red giant sun will be thousands of times what it is today, enough to vaporize the oceans, strip away the atmosphere, and melt the surface of our planet into a sea of magma. Mercury will be consumed. Venus will be consumed. Earth will be sterilized and possibly consumed. Mars will survive but will be baked. The red giant phase will last approximately 1 billion years. During this time, the helium core continues to contract and heat until, at a temperature of about 100 million degrees, helium fusion ignites in the core, the triple alpha process which fuses 3 helium nuclei into 1 carbon nucleus. This phase of helium burning is relatively brief, about 100 million years. When the helium is exhausted, the sun will not have enough mass to fuse carbon or heavier elements. its core will contract one final time, while the outer layers are gently expelled into space, forming a beautiful, glowing shell of gas called a planetary nebula, one of the most visually stunning objects in astronomy, despite the misleading name. A planetary nebula has nothing to do with planets. It is the dying breath of a star. Planetary nebulae are among the most photographed objects in astronomy. The Ring Nebula, the Cat's Eye Nebula, the Helix Nebula, all are the remnants of stars similar to our Sun, caught in the act of shedding their outer layers. Each one is unique, shaped by the star's rotation, magnetic field, and the presence of companion stars, but all share the same basic structure, a glowing shell of expelled gas surrounding a tiny, intensely hot central star. The planetary nebula phase is brief, lasting only about 10 to 20,000 years before the ejected gas disperses into the interstellar medium. But during that brief time, the nebula glows with extraordinary beauty, lit by the ultraviolet radiation from the still hot central star. If any civilization in a distant star system were watching our Sun 5 billion years from now, they would see a brief, luminous flower bloom in the sky, the Sun's final gift to the cosmos, before it faded and the light went out. At the center of the planetary nebula, the exposed core of the Sun will remain a dense, Earth-sized ball of carbon and oxygen called a white dwarf. A white dwarf has roughly the mass of the Sun compressed into a volume no larger than Earth. A teaspoon of white dwarf material weighs about 5 tons. The white dwarf will initially be very hot, perhaps 100,000 degrees, and will glow with a brilliant white-blue light, but it has no internal energy source. It will slowly cool and dim over trillions of years, eventually fading to a dark, cold cinder called a black dwarf, though the universe is not yet old enough for any black dwarfs to exist. The time required for a white dwarf to cool to invisibility is estimated to be at least 10 to 15 trillion years, roughly 1,000 times the current age of the universe. This is the Sun's future. Birth in a cloud of gas. 4.5 billion years of steady hydrogen fusion. A dramatic expansion into a red giant that destroys the inner planets. A gentle death as a white dwarf slowly cooling in the darkness. And then silence. An ember in the void, carrying the carbon forged in its core. Carbon that was once part of planets, that was once part of living things, that was once us. There is a strange beauty in this timeline. The Sun will spend its first 10 billion years as a main sequence star, stable, reliable, life-sustaining. Then it will spend about 1 billion years as a red giant, violent, luminous, destructive. Then about 100 million years burning helium. Then 20,000 years as a planetary nebula. And then trillions of years as a white dwarf, slowly, silently, cooling in the dark. The proportions are striking. The active, energetic, world-building phase of the Sun's life occupies a tiny fraction of its total existence. For most of its future, trillions upon trillions of years, the Sun will be a cold, dark remnant, a memory of fire, a fossil of light. This puts our own existence in perspective. We live during the Sun's brief, glorious Middle Age, the window of time when it is hot enough to sustain life, but not yet so hot that it destroys it. This window is finite. It began when the first life appeared on Earth, roughly 3.8 billion years ago, and it will end when the increasing luminosity of the aging Sun makes Earth uninhabitable, roughly 1 billion years from now. Our window of habitability is about 4.8 billion years wide, a long time by human standards, but a small fraction of the Sun's total lifespan. We are not permanent residents of this solar system. We are guests staying during the comfortable season in a house that will eventually be torn down. Everything we know, everything we love, everything we build, it all exists within this window. This brief interval of warmth between the cold of the primordial past and the cold of the distant future. But let us not mourn the sun's eventual death. Let us marvel at its generosity. Because everything you have ever known, everything you have ever touched, everything you are, exists because of the sun. Not just in the obvious way, not just because the sun provides light and warmth. In a far deeper, more fundamental way, the atoms in your body, the carbon in your muscles, the calcium in your bones, the iron in your blood, were forged inside stars, not our sun. Our sun is not massive enough to produce elements heavier than carbon and oxygen. But previous generations of stars, stars that lived and died before our sun was born, fused hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron, in a chain of stellar nucleosynthesis that built the periodic table element by element. When those stars exploded as supernovae, they scattered their newly forged elements across space. Those elements became part of the molecular cloud that collapsed to form our sun and our solar system. And our sun is not just any star in any location. It orbits the center of the Milky Way at a distance of about 26,000 light-years, completing one orbit every 230 million years, a period sometimes called a galactic year. The sun has completed about 20 orbits since it was born. Its position in the galaxy is itself significant. We sit in the galactic habitable zone, far enough from the center to avoid the intense radiation and gravitational disruptions of the galactic core, but close enough that the gas and dust needed for planet formation were available. The sun's orbit is also remarkably circular compared to many stars, meaning it does not plunge into the dense, dangerous inner regions of the galaxy or drift out into the sparse outer disk. Whether this orbital stability contributed to the long-term habitability of Earth, 4 billion years of uninterrupted biological evolution, is a question that astrobiologists are still exploring. You are made of star stuff. This is not a metaphor. It is a literal, physical fact. The iron in the hemoglobin molecules that carry oxygen through your bloodstream was forged in the core of a massive star that exploded billions of years before the sun was born. The oxygen you are breathing right now was created by nuclear fusion in a star that no longer exists. The carbon atoms that form the backbone of your DNA were assembled in the heart of a red giant that died so that you could live. And our sun, carrying on the tradition, has taken those raw materials and provided the energy to assemble them into something extraordinary. Liquid water, organic molecules, cells, organisms, minds, consciousness, you. The sun does not just light the world, it created the conditions for the world to exist. It drives the water cycle that fills our rivers and oceans. It powers photosynthesis, which is the foundation of nearly every food chain on Earth. It drives the atmospheric circulation that creates our weather. It warms the surface enough to keep water liquid, the essential medium for life as we know it. Without the sun, Earth would be a frozen ball of rock and ice, drifting in darkness, lifeless and silent. And yet, as we have seen tonight, the same sun that gives us everything can also take it all away. A single well-aimed coronal mass ejection could devastate our technological civilization. A long-term change in solar output could alter our climate. And in the distant future, the sun's inevitable expansion will erase every trace of life from the inner solar system. This is the paradox of our star. It is both our creator and our destroyer, our nursemaid and our executioner, the source of all life and, eventually, the cause of all death on this planet. There is no escaping this relationship. We are bound to the sun, literally, gravitationally, electromagnetically, chemically, biologically, in a bond that began when the first atoms of our bodies were forged in its predecessors, and that will end only when the sun itself dies. The sun even plays a role in the geology of our planet. The tidal forces from the sun, combined with those from the moon, create the ocean tides. The sun's tidal contribution is about 46% of the moon's, but when the sun, moon, and earth align, during full and new moons, the tidal forces combine to create spring tides, the highest tides of the month. These tides have shaped coastlines, driven the evolution of intertidal organisms, and influenced human history, from fishing patterns to naval battles to the timing of D-Day. The sun also drives the water cycle. Solar energy evaporates water from the oceans, lifting it into the atmosphere as water vapor. The vapor condenses into clouds, is carried by winds, which are themselves driven by differential solar heating of Earth's surface, and falls as rain or snow, filling rivers and lakes and aquifers. Every glass of water you drink, every crop that grows in a field, every river that flows to the sea, all are powered, ultimately, by the sun. The water cycle is a solar engine, converting the sun's radiant energy into the movement of water across the surface of the planet. And photosynthesis, the foundation of nearly all life on Earth, is a direct solar technology. Plants, algae, and cyanobacteria capture photons of sunlight and use their energy to split water molecules, releasing oxygen and fixing carbon dioxide into organic molecules. This process produces the oxygen we breathe and the organic matter that feeds virtually every food chain on the planet. The fossil fuels we burn, coal, oil, natural gas, are stored solar energy, captured by photosynthetic organisms millions of years ago and concentrated in the Earth's crust. When you drive your car or turn on a light, you are using ancient sunlight. Even renewable energy technologies are solar derivatives. Wind power works because the sun heats the atmosphere unevenly, creating pressure differences that drive winds. Hydroelectric power works because the sun evaporates water, which falls as rain and fills reservoirs. Only nuclear and geothermal energy are truly independent of the sun. And even geothermal energy is partly powered by radioactive elements that were forged in the same stellar processes that created the sun. The sun is not just a light in the sky. It is the engine that drives the entire biosphere, the machine that makes Earth work. Let us spend a few more moments thinking about what the sun means in the broader context of the universe. Because our sun, as extraordinary as it is to us, is a profoundly ordinary star. The sun is classified as a G-type main sequence star, specifically a G2V star. It is a yellow dwarf, though calling it yellow is somewhat misleading. Its peak emission is actually in the green part of the spectrum, and it appears white when viewed from space. From Earth's surface, atmospheric scattering shifts its apparent color toward yellow, especially at low angles. In terms of brightness, the sun falls in the middle of the stellar range. There are stars hundreds of thousands of times more luminous, blue supergiants like Rigel, which outshines the sun by over 100,000 times, and stars thousands of times dimmer, red dwarfs like Proxima Centauri, which emits less than 1,000th of the sun's light. In terms of mass, The Sun is slightly above average for a star, but well below the most massive stars known. The most massive stars can be over 200 times the Sun's mass. The least massive are about 8% of the Sun's mass. Any less, and they cannot sustain hydrogen fusion. In terms of age, the Sun is middle-aged. At 4.5 billion years, it is roughly halfway through its main sequence lifetime of about 10 billion years. It is a mature star, neither young and reckless nor old and fading. The Sun's position in the Milky Way galaxy is worth noting. We orbit the center of the galaxy at a distance of about 26,000 light-years, roughly halfway between the galactic center and the outer edge. Our orbital speed around the galaxy is about 220 kilometers per second, and it takes us approximately 230 million years to complete one orbit, a period sometimes called a galactic year. The Sun has completed about 20 orbits around the Milky Way since it was born. Our position in the galaxy may be significant for habitability. We orbit in what some astronomers call the galactic habitable zone, far enough from the galactic center that we are not bombarded by the intense radiation from the central supermassive black hole and the dense clusters of stars near it, but not so far out that the heavy elements needed to form rocky planets and complex chemistry are scarce. We are also fortunate to orbit between the major spiral arms of the galaxy in a relatively quiet inter-arm region where the density of stars is lower and the risk of nearby supernova explosions is reduced. Whether this galactic position is a coincidence or a requirement for the development of complex life is an open question. But it is another way in which the Sun and its place in the cosmos seems oddly, perhaps suspiciously, well suited for life. And yet, despite being cosmically ordinary, the Sun has done something extraordinary. It has sustained the conditions for life on one of its planets for over 3.5 billion years. It has provided a stable, reliable energy source for an almost incomprehensible span of time, long enough for single-celled organisms to evolve into creatures that can build telescopes and launch spacecraft into the Sun's own atmosphere. Whether this is rare or common in the universe, we do not yet know. But we know it happened here, and that is enough to make our ordinary star the most important object in our sky. There is a concept in astronomy called the circumstellar habitable zone, sometimes called the Goldilocks zone. The range of orbital distances from a star where temperatures allow liquid water to exist on a planet's surface. Our Sun's habitable zone extends from roughly 0.95 to 1.4 astronomical units. Earth orbits at 1 AU comfortably within the zone. Venus at 0.72 AU is too close. Its surface temperature is over 460 degrees. Mars at 1.52 AU is near the outer edge and might have been habitable with a thicker atmosphere. But the concept of a habitable zone is more nuanced than simple distance. The zone shifts over time as the star's luminosity changes. Early in the Sun's life, when it was 30% dimmer, the habitable zone was closer to the star. Earth may have been near the outer edge of the habitable zone, and Mars would have been well outside it. Yet we have evidence that both planets had liquid water in the distant past. This is the faint young sun paradox, the puzzle of how Earth and Mars could have been warm enough for liquid water when the Sun was significantly dimmer than it is today. The best current explanation involves greenhouse gases. Early Earth likely had a much thicker atmosphere rich in carbon dioxide and possibly methane, which trapped enough solar energy to keep temperatures above freezing despite the fainter sun. Mars may have had a similar CO2-rich atmosphere during its wet period. As the Sun gradually brightened, Earth's carbon cycle, a feedback mechanism involving volcanoes, weathering, and plate tectonics, adjusted the atmospheric CO2 concentration to maintain roughly stable temperatures. Mars, lacking plate tectonics, had no such feedback mechanism, and when its atmosphere was stripped away, there was no way to compensate. This long-term dance between the Sun's increasing luminosity and Earth's atmospheric regulation is one of the most remarkable features of our planet's history. The fact that Earth has maintained liquid water on its surface for over 4 billion years through a 30% increase in solar luminosity is a testament to the extraordinary resilience of the Earth system. But that resilience has limits. As the Sun continues to brighten, the carbon cycle will eventually be unable to compensate. CO2 levels will drop below the threshold needed for photosynthesis. Plant life will die. The biosphere will collapse. And eventually, the increasing solar heat will overwhelm even the reduced greenhouse effect, evaporating the oceans and turning Earth into a Venus-like world. This will happen in roughly 1 billion years, a long time by any human measure, but a reminder that our window of habitability is finite, and that it is the Sun, ultimately, that determines how long that window stays open. There is another way to think about the Sun's relationship to life, one that borders on the philosophical. The Sun is a second-generation star, possibly third generation. It formed from material that had already been processed through at least one previous stellar cycle. Material enriched with heavy elements forged in the cores and explosions of earlier stars. The Sun inherited carbon, nitrogen, oxygen, silicon, iron, and dozens of other elements from its stellar ancestors. In a very real sense, the Sun is a phoenix, risen from the ashes of dead stars. And it, in turn, when it dies billions of years from now, will scatter its processed material back into the interstellar medium, where it will become part of the raw material for new stars and new solar systems. Our Sun's carbon and oxygen, some of which will have been forged in its own core during the helium-burning phase, will drift through space for millions of years before being swept up into a new molecular cloud, a new collapse, a new stars. The cycle is endless. Stars form, live, die, and fertilize the next generation. The universe builds complexity through stellar recycling, each generation of stars producing heavier elements, enriching the cosmic environment, making possible the chemistry that leads to planets and life. Our Sun is one link in a chain that stretches back to the first generation of stars, born from pure hydrogen and helium in the aftermath of the Big Bang, and forward to stars that will not exist for billions of years. We are part of that chain too. The atoms in our bodies will outlive us, outlive the Sun, outlive the solar system. They will be recycled into new stars, new planets, perhaps new life. In the deepest possible sense, we are the universe experiencing itself, star stuff, contemplating stars. There is one more thing worth knowing about the Sun, something that connects the cutting edge of physics to the nuclear furnace at the heart of our star. It is the story of the missing neutrinos, a mystery that took 30 years to solve and earned 2 Nobel Prizes. Remember the proton-proton chain reaction we discussed earlier. One of the byproducts of that process is neutrinos, ghostly, nearly massless particles that barely interact with ordinary matter. The Sun produces about 2 times 10 to the power of 38 neutrinos per second. These neutrinos stream outward at nearly the speed of light passing through the sun's entire body as if it were not there. They arrive at Earth about 8 minutes after being created, and about 65 billion of them pass through every square centimeter of your skin every second. In the 1960s, Raymond Davis Jr. built the first detector capable of catching solar neutrinos, a tank filled with over 380,000 liters of perchloroethylene, a dry cleaning fluid buried deep underground in the Homestake gold mine in South Dakota. The underground location shielded the detector from cosmic rays which would produce false signals. Davis ran his experiment for over 30 years, and from the very beginning, he found a problem. His detector was catching only about 1/3 of the neutrinos predicted by the standard solar model. 2/3 of the expected neutrinos were missing. This became known as the solar neutrino problem. Either the standard model of the sun was wrong, meaning we did not understand how the sun works, or something was happening to the neutrinos between the sun and the detector. The answer, when it finally came, was stunning. The neutrinos were not missing. They were changing. Neutrinos come in 3 types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. The sun produces only electron neutrinos. Davis's detector was designed to catch only electron neutrinos. But as the neutrinos traveled from the sun to the Earth, they were oscillating between flavors, a quantum mechanical phenomenon called neutrino oscillation. By the time they reached the detector, 2/3 of them had transformed into muon or tau neutrinos, which the detector could not see. This was confirmed in 2001 by the Sudbury Neutrino Observatory in Canada, which was designed to detect all 3 flavors. It found that the total number of neutrinos arriving from the sun matched the predictions exactly. The missing neutrinos had been there all along, just in a different form. The story of the solar neutrino problem is a beautiful example of how science works at its best. For 30 years, a discrepancy existed between observation and theory. Most scientists assumed the observations were wrong, that Davis's experiment was somehow flawed. Some proposed that the standard solar model needed adjustment. A few bold theorists, including Bruno Pontecorvo, who had first proposed the idea of neutrino oscillation back in 1957, suggested that the problem lay not with the sun or the detector, but with our understanding of neutrinos themselves. It took 3 decades to build the technology needed to test this idea. The Sudbury Neutrino Observatory used 1,000 tons of heavy water, deuterium oxide borrowed from Canada's nuclear energy program, contained in a transparent acrylic sphere 12 meters in diameter, surrounded by nearly 10,000 photomultiplier tubes, all buried 2 kilometers underground in an active nickel mine. The experiment cost over 300 million Canadian dollars and took nearly a decade to build. But when it turned on and the data came in, the answer was clear and unambiguous. The total neutrino flux from the sun matched the theoretical prediction. The electron neutrinos were oscillating into muon and tau neutrinos during their 8-minute journey from the sun. The solar model was right. The particle physics was wrong, or rather, incomplete. The resolution of the solar neutrino problem had profound implications beyond solar physics. Neutrino oscillation requires neutrinos to have mass, a property that the original standard model of particle physics did not allow for. The discovery of neutrino mass was a crack in the standard model, a sign that our understanding of fundamental physics is incomplete. Raymond Davis and the leader of the SNO experiment, Arthur MacDonald, shared the Nobel Prize in Physics in 2015 for their work. And so the sun, our familiar everyday star, contributed to one of the most important discoveries in fundamental physics. A discovery that told us something deep about the nature of matter itself. The sun is not just a source of light and heat. It is a laboratory, a particle accelerator, a testing ground for the laws of physics operating under conditions we can never replicate on Earth. There is one more solar mission worth mentioning before we begin our closing reflections, because it represents a different approach to studying our star. While Parker's solar probe approaches the Sun from close range, the Solar Orbiter, a joint mission between ESA and NASA, launched in February 2020, studies the Sun from an oblique angle using gravity assists from Venus and Earth to tilt its orbit out of the ecliptic plane. This allows Solar Orbiter to see the Sun's poles for the first time, regions that are impossible to observe from Earth or from spacecraft in the ecliptic plane. The Sun's poles are of intense scientific interest because they play a crucial role in the solar cycle. The polar magnetic field at solar minimum serves as the seed for the next cycle's activity. A stronger polar field generally predicts a more active next cycle. But we have never been able to observe the polar regions directly. Our understanding of polar magnetism comes entirely from models extrapolated from equatorial measurements. Solar Orbiter's images from its first high-latitude passes have already revealed unexpected features, small-scale magnetic structures, and polar bright points that were not predicted by models. As the mission continues and the orbit tilts further, eventually reaching inclinations of over 30 degrees above the ecliptic, scientists hope to gain their first direct view of the Sun's polar magnetic field, potentially revolutionizing our understanding of the solar cycle. Between Parker's solar probe approaching the Sun from within and Solar Orbiter observing from above, we are entering a new era of heliophysics, one in which we can see the Sun from perspectives that were literally impossible just a decade ago. The Sun, which has dominated human experience since the first dawn, witnessed by the first human eye, is finally revealing its secrets. And what we have learned is both reassuring and humbling. Reassuring because the Sun is fundamentally stable, a steady, reliable energy source that has sustained life on Earth for billions of years. Humbling because that stability coexists with a capacity for violence that could, at any time, remind us how fragile our technological civilization really is. Tonight, we have traveled from the Sun's core to its corona, from its violent past to its distant future, from the smallest particles it produces to the most destructive storms it unleashes. We have seen a star that is simultaneously mundane and extraordinary, a middle-aged, medium-sized yellow dwarf that happens to be the single most important object in the lives of every human being who has ever lived. The sun will rise tomorrow morning, as it always does. You will feel its warmth on your skin and probably not think about it at all. That is fine. That is human. We take for granted the things that are always there. But tonight, for just a moment, you know better. You know that the warmth on your skin began as a nuclear reaction 15 million degrees hot, fought its way through 100,000 years of plasma, crossed 150 million kilometers of empty space in 8 minutes, and arrived at your face carrying the energy of 4 million tons of annihilated matter per second. You know that the star that warms you could also destroy your civilization with a single, well-aimed eruption. You know that it is slowly, imperceptibly getting brighter, and that in 1 billion years it will make Earth uninhabitable, and in 5 billion years it will swallow the inner planets whole. And you know that it will die, that this fierce, furious, generous engine of light will one day exhaust its fuel, swell and redden, shed its outer layers into space like a flower scattering its petals, and collapse into a white dwarf the size of Earth, a dim ember that will cool for trillions of years until even it goes dark? But that is so far in the future that the word future barely applies. For now, the sun burns. It lights our world, drives our weather, feeds our crops, powers our lives, and asks nothing in return. It has been doing this since before the first cell divided in a primordial ocean, and it will continue doing it long after the last traces of our civilization have turned to dust. So let tonight be quiet. Let the weight of the day lift from your shoulders. Let your thoughts drift upward, through the atmosphere, past the magnetic field that shields you, past the solar wind that flows endlessly outward, past the orbits of the inner planets, toward that vast, brilliant, terrifying, beautiful star that makes all of this possible. The sun is not just a star. It is our star. And for a little while longer, a few billion years, give or take, it will keep the lights on for us. That is more than enough. That is everything. Good night. Sleep well. And tomorrow, when the sun rises, take a moment, just one moment. Look up. Not directly, never directly, but toward the light. Feel it on your face, and know, for just a second, what it really is. A controlled thermonuclear explosion, 93 million miles away, that has been burning for 4.5 billion years, converting 4 million tons of itself into pure energy every single second, so that you can stand here on this small blue world and feel warm. That is the sun, and it is the most extraordinary, ordinary thing in the universe.